I can see 4 people. It's enough for us to start. If you can hear me, we can start. Please, you can hear me. Let me get this in the chat box so that we can start immediately. Can you hear me? Can you hear me? Well, please, if you can hear me, respond to the chat box so that we can move forward. Well, West, okay, you can hear me. Somebody has responded. So please, I want to, if you can hear me, I want to share this screen. It is your textbook, so I want us to be looking at it. For those who doesn't have it, for those who doesn't have it, we'll look at it together. So, um, so looking at the, so this is your textbook. The topic we'll be treating today is momentum. Momentum. Okay. Please, can you see the textbook? Please. Can you see the textbook I shared? Can you see it? Your textbook, I just shared it. Can you see it? If you can see, let me know so that we can. Okay. Somebody say sure. So it means we are good to go. So looking at this, we want to talk about linear momentum. From what we have discussed in the class, we know that linear momentum is a product of the mass and its velocity. The product of the mass and its velocity. So as you can see, we have an example. Our interest here is the calculation. is a calculation. So look at example 4.1. Calculate the momentum of the following object. A golf ball of mass 0.20 kg traveling at 20 meters per second. B. A truck of mass 1000 kg moving with a velocity of 15 meters per second. There are two questions there. The first one, a golf ball of mass 0.20 kg. So the mass is given there. As you can see, the mass is given and the velocity is given. This question is direct. But what I want, please let me be sure that you are seeing it. Please let me be sure that you are seeing the book and you are following. Somebody said the book is not clear. But you have your own there. If you have your own textbook there, you can follow from there why I explain here. You have your textbook with you so that I can explain from there. If you have your textbook with you, let me know because I want to explain certain things that are very essential and they will be very useful to you. So please respond if you have there your own. If you don't have, we'll manage this one. Do you have? You have your textbook. You are supposed to be at home, so your book should be with you. This is, I think, just after 9. Okay, you have the book. Um, it's a power failure. Just a minute. Let me on the backup flights. Okay. Sorry about that. There was a power failure. So let's okay, somebody say yes. So let's look at it. Please, if you cannot hear me or you don't understand anything, send a message on the chat box. Send a message on the chat box so that I can um, get to understand what is the problem. So, just like I was explaining, you have this, and the interest here is that looking at example 4.1, that is what we are looking at. So we have two questions here, and this question seems to be direct. It seems to be direct in the sense that the mass and the velocity are given. For the first one, the mass is 0.20 kg, and then the second one, the mass is 1000 kg, while the velocity is 15 meters per second. These are direct questions. But assuming these are not given direct, what do you do? Or assuming the units are not given in SI units, what do you do? you will need to convert the necessary unit. These are the things I normally emphasize. So you multiply the mass and the velocity, and the answer is in kilogram meter per second. And in your options, the answer, for example, the A part is 4 kilogram meter per second. It may be 4 with a different unit, so always take notes of the units. You must get the figures correctly, but the units, if you don't get it right, you fail the question. So the emphasis, the technicalities here is you should be familiar with the units of what you are calculating. So those questions direct. So and 4.3 you have Newton's second law of motion and linear momentum. We have explained this. We have explained this. Okay, somebody said maybe you can be reading the questions slowly for us. Okay, I think you have the textbook there now. You should have the textbook there. So there's no point copying. Just take notes of the necessary uh, points that I'll be making. Just take note of the necessary things that I'll be making. So just a minute, let me. So you you should take note of this. So looking at the 4.3, section 4.3, we'll talk about Newton's second law of motion and linear momentum. Newton's second law of motion states that this is the mathematical expression. Force, the rate of change of momentum is directly proportional with the applied force. And what is momentum? Product of mass and its velocity. So it's possible we have the final momentum and the initial momentum. So the difference between the final momentum and the initial momentum is what we call the change in momentum. And that is what you are seeing here where the arrow is moving. mv is the final momentum while mu is the initial momentum. And the difference between the two is what we call the change in momentum. So we know that Newton's second law of motion can be written as F is equal to ma. I even made a video on this, and you can go back and watch that video, how this formula is derived. So the question here is a boy pushes a stationary toy car with a horizontal net force of 1.5 Newton for 0.2 seconds. The toy car has a mass of 0.15 kg. Calculate A, the final momentum, B, the final velocity. Looking at these parameters, we have force given as 1.5 Newton, U, the initial velocity, stationary, starting from or stationary means U is 0 and T is this, while the second mass, the mass is given as 0.15. So we can loosen the formula F is equal to mv minus mu all over T. F is given And what we are calculating is the final momentum. We know the initial momentum. So from here, you can make mv the subject. And by the time you make mv the subject, mv is equal to 1.5 times 0.2 second, and that gives us 0.3 kilograms per. Please, if you are not following what I'm saying, you can let me know on the chat box. But if you are following, you tell me you are following. I hope you are following. I hope you are following. So let me know so that we can make progress. Please, I'm waiting for your response so that we can make progress. Okay, somebody said yes. So let's make progress. So looking at this, the B part of the question is calculate the final velocity. And then from here, we have mv is equal to this. That is the initial momentum, or the final momentum we calculated is mv is equal to 0.3 kg. So from here, if you make v the subject, v becomes this figure divided by m. And the m is given as 0.15 kg, which will give us this. In this whole thing, want to the examiner want to test how smart you are, want to test the level of on your understanding, how you can play around with these figures, how you can identify the given parameters and be able to also identify the formula you have to use, and then the answer you get and the correct unit. Yeah, these things are very, very important. So if you are with us, let's move on. Let's move on. So looking at the impulse. Impulse is the same thing as force times time, and that impulse is that impulse is equal to the change in momentum. So from here, you can see that impulse is equal to the force. Look at equation 4.6. Impulse. If you are asked to calculate impulse, impulse is equal to force times change in time. And sometimes, if you calculate the change in momentum, that figure is equal to the impulse. What is change in momentum? The difference between the final momentum and the initial momentum. So, and it is equal to the force times the change in time. So the summary is that the impulse is force times time. So look at the example 4.3. A stationary baseball is struck by a bat with which exerts a force of 35 Newton for 0.05 seconds on it. Calculate the impulse given to the ball. Calculate the impulse given to the ball. Here, what we are given is the force and the time. Ask yourself, the force, is it given in the SI unit? The time, is it given in seconds? If the answer is yes, you can go ahead and calculate your impulse, which is equal to F times T, which is 35 times 0.05, which gives us the answer in 1.75 newtons seconds in the direction of the force. In the direction of the force. So if you are following what you are doing, okay, somebody say, I dropped my textbook at home and I went to block A to read before I discovered there's a class. Okay, that is not a problem. I hope you are seeing this, and if you are seeing this, we can move on. We can move on. So there are certain things I want you to have at your fingertips. So look at your example 4.4. Example 4.4. A car of mass 200 kg moving with a speed of 30 meters per second was suddenly hit by another car moving in the same direction. What is the impulse received speed attained at the same time of the impact is twice as its initial speed? This question looks technical, but it is simple. Let me repeat the question again. A car of mass 200 kg moving with a speed of 30 meters per second was suddenly hit by another car moving in the same direction. Those two cars are moving in the same direction. What is the impulse received by the first car if the speed attained at the time of impact is twice its original speed? So look at the explanation here. Look at the explanation here. The mass m of the car A is 200 kg, initial speed 30 meters per second, final speed is 2u, 2 times the original speed. What is the impulse? Impulse is change in momentum. Impulse is equal to change in momentum, which is equal to mv minus mu. So since we have the two velocities, the final and the initial, we can say that impulse, the change in momentum is 200 minus into 60 minus 30. And if you multiply this, it means you are multiplying 200 by 30, which will give us um, 6,000 Newton. There should be a typographical error there. Can you see it? There should be a typographical error, because if you multiply 6, to multiply 200, by 30, that will give you 6,000 and not 600 Newton. Please correct this, please. If you have your pen there, correct it. Multiply 200 by 30, because 60 minus 30 is 30. Multiply by 200 should give you 6,000 Newton. Hope you can. Okay. So let's if you can correct that, you can make progress. So these are the questions. These are the questions. There's another one here. This thing is about calculations. A ball of mass 0.75 kg is dropped from rests from a height of 45 meters above the concrete floor. The impact of the ball on the concrete floor takes 0.5 seconds. The ball rebounds to a vertical height of 5 meters above the concrete floor. Find A, the impulse of the concrete floor on the ball, and B, the average force on the ball. So looking at this, the ball is from rest, hitting this will rebound back. So if you let the initial velocity and the final velocities before rebounds be u1 and v1 respectively, as you can see. So using the equation of motion, we can calculate v1, and which is, if you take the square root of 900, it will give you 30 meters per second. So we can also calculate u2 from this, because this one is going against gravity, and that's the reason why we have minus here, because if it bounces and it's moving up again, it's going against gravity. So you have minus 2 times 10 raised to power 2 times 10 times 5, which will give us, to take the square root of 100 will give you 10. Therefore, impulse is equal to change in momentum. So by the time you do this, you have minus 30 newton second, because this is moving against gravity. So these are the, if you have any issue with this explanation, you let me know. Any issues so far? Any issues so far? So we will move on. We have what we call the principles of conservation of linear momentum. The principle of conservation of linear momentum states in any system of colliding bodies, the total momentum before collision is equal to the total momentum after collision, provided no external force acts on the colliding bodies. That is the principles of conservation of linear momentum. If you have two colliding bodies, if momentum and kinetic energy are conserved, then we're talking about the we have two types of collision. We have what we call the elastic collision and inelastic collision. So if momentum and kinetic energy are conserved, then we talk about elastic collision. But if only momentum is conserved, then we'll talk about inelastic collision. So we know that momentum is product of mass and its velocity. So the momentum before collision must be equal to the momentum after collision. And that is the principles of conservation of linear momentum. So if you look at this, if you look at this expression, this is before collision. You can see my arrow. Ma is the mass before collision. Ua is the initial velocity of body Ma. Then Mb, Ub. These are the two masses. So upon collision, then after collision. So the momentum before and the momentum after collision are equal. That is the conservation of linear momentum. So like I explained before, we have two types of collision. We talk about the elastic collision and inelastic collision. So the calculations here are very simple, at the same time technical. But I wouldn't want to bother you because we didn't start early. We will stop here. We'll stop here and we'll stop here and I want you to ask your questions. Ask your questions. So the collision. Now, if you look at this, we have an example here. That is example 4.6. Example 4.6. A ball P of mass 0.5 kg. Example 4.6. If you can see that, a ball P of mass 0.5 kg and a velocity 10 meters per second collides with a stationary ball Q of mass 0.3 kg. After the collision, ball P continued to move in the same direction at 30 meters per second. A. What is the velocity of the ball Q? B. What will be the velocity of ball Q if ball P were to move in the opposite direction at 1 meter per second after collision? I repeat this question again. I repeat that question again. Example 4.6. A ball P of mass 0.5 kg and velocity 10 meters per second collides with a stationary ball Q of mass 0.3 kg. After the collision, the ball P continues to move in the same direction at 30 meters per second. There are two questions here. First one, what is the velocity of ball Q? Question 2, which is B, what will be the velocity of ball Q if the ball P were to move in the opposite direction at 1 meter per second after collision? Need to pay attention here. When you look at this, When you look at this question properly, the solution, we know that P has a mass of 0.5, the initial velocity is 10. Q has a mass of 0.3, the initial velocity is 0 because it is stationary. You need to take note of that. That's 0 because it is stationary. Then after collision, the mass is still the same, but the velocity will change, or P change to 3 meters per second, and the mass of Q is still 0.3, and the velocity is what we are looking for. So if looking at the conservation of linear momentum, you have MP UP plus MQ UQ equal to MP VP plus MQ VQ. And what you are calculating here is VQ. So if you do the substitution and make VQ the subject of the formula, you now have 11 meters per second. Then the other question say if they move, the other mass move in the opposite direction after collision. So in that case, you have this, and then you make VQ the subject of the formula, you have 18.3 meters per second. So we'll stop here. Then tomorrow we'll start with collisions. Tomorrow we still have this class. Those of you that uh, have interest in this, you shouldn't give up. By tomorrow, we'll have the class by the same time, 8:30. And tomorrow we'll be discussing the collision, the types of collision, the elastic and inelastic collision. So if there's any question, you can ask. If there's any question, you can ask. If there's none, so we'll end the class here and then resume tomorrow by 8:30.